All right, good. All right, so let's get started. My name is Mike Carew. I'm part of the organizing committee for the 20 Collegeville workshop on scientific software with an emphasis on developer productivity. And I have here today 4 of the leading people in design of numerical software. And all of them are involved in trying to provide performance, portability, and efficient back-end footprints as we move into the era of heterogeneous computing. So, well, we're already there, but as we continue to expand the number of heterogeneous compute devices that we need to use. For those of you who haven't maybe been paying a lot of attention, heterogeneity is one of the design parameters that we have available to us as clock speeds have slowed down and other improvements to processor design have started to run out. And so we anticipate over the next years, decade or so at least, that these heterogeneous devices, which then provide a biased improvement towards say one type of communication computation pattern versus other types, are going to be a new trick or one of the stronger tricks that we have to play going forward. And so these efforts, these 3 efforts that we'll talk about today, are attempts to provide good software design and adaptability and performance in the presence of increased heterogeneity. And so to get started, we'll have each team talk a bit about their approach and the design priorities they're trying to address. And then we'll move into a discussion of where each of these approaches might be really strong and where maybe they wouldn't necessarily be the right choice outside of the domain that each of these teams has picked for doing their work. So let's get started first by doing a bit of introduction. Maybe just quickly say who you are and where you're from and what effort you represent. Hartley, let's start with you. Yeah.
Thank you, Mike. Yeah, my name is Hartley Gans. I'm a junior research group leader at the Cultural Institute of Technology, and I'm also a research scientist at the University of Tennessee in Jack Dongar's group. And what I'm doing in my research is developing sparse linear algebra libraries and algorithms for modern HPC architectures, particularly GPUs. And the product that I'm representing here is the Ginkgo software library. Ginkgo is a single node sparse linear algebra library. And when designing Ginkgo, we asked ourselves first, so what makes a software library sustainable? And of course, there are software libraries that have a lifetime that is much longer than a single architecture. And there are software libraries that fade out. And when looking at the reasons, we figured out that usually the reason why software libraries fade out is actually that they fail to jump to the next hardware architecture. It's often not the design or the algorithms or the performance. It's simply that the jump to the next architecture is too big. And keeping that in mind, we put performance or portability, architectural portability at the core of the Ginkgo library. And the approach that we took is that we radically separate the algorithms that are generic from the backends. And the backends are basically the kernels for a specific architecture. That, of course, implies a lot of effort. On the one side, we have to keep the core updated and add new algorithms to the core. And also, whenever there's a new architecture rising on the horizon, we have to generate kernels and write kernels for that specific architecture. So currently, we support Intel multi-core CPUs with OpenMP. We support NVIDIA GPUs using NVIDIA CUDA, and we support AMD GPUs using the HIP programming ecosystem. And we're looking forward into putting together a backend for Intel GPUs. So this approach allows for easy extension. So it's easy to add new architectures, and it's also easy to remove old architectures that we don't need anymore.
Thank you. Very nice. Let's move on then to Siva and Nathan. You want to introduce yourselves briefly, and then we'll let you talk a little bit about the approach you're using.
I'm Siva Rajamanikam. I work at Sandy National Labs at Albuquerque office. I represent the Cocos kernels ecosystem here, along with Nathan. There are two of us who represent Cocos and Cocos kernels here. In terms of background, I come from the computer science background with a heavy emphasis on linear algebra, sparse linear algebra especially. I also work on machine learning projects, which gives me a different perspective on how that community looks at portability on different architectures, how they tackle to run frameworks on different machine learning hardware and GPUs, right? And in terms of Cocos's philosophy, we would like both performance, portability, and productivity, which goes very well with the theme of this conference. We would, our focus always is how to write large scale applications efficiently over many years, easily maintainable for performance and for portability, right? So to help to scale it up to a lot of developers, a lot of applications. I let Nathan talk about individual aspects of Cocos that are unique to what we do.
So I'm Nathan Ellingwood. Yeah, thanks, Siva.
Go ahead.
Thanks, Mike. I'm Nathan Ellingwood. I'm a senior member of technical staff at Sandia, and I also work with Siva and here representing the Cocos ecosystem. A couple of things, I guess, to mention about Cocos is that to facilitate some of this portability and performance aspects, there's abstractions between data structures and parallel execution that are provided in the Cocos core library. These help to facilitate the performance portability aspects. And then separately, there's the Cocos kernels library where we can write low-level kernels for things like linear algebra loss or sparse or dense loss or graph kernels that are built on top of Cocos. And that's another aspect that helps with the performance portability aspects.
Yeah, very good. Thank you. Hi, Piotr. You want to go next?
Yes. Okay. So my name is Pierre Luschek. I am the research assistant professor at the University of Tennessee and the Knoxville campus. And I work at the Jack Dongaris group. It's called ICL, Innovative Computing Lab. And on my day-to-day work involves benchmarking and numerical linear algebra libraries. And today I'll be representing the latter, and in particular, the numerical linear algebra library I'd like to represent is Plasma, which has been around since around 2006. So as Hartwig mentioned, it's software usually survives hardware, and the hardware gets in a way retired. So Plasma started as a multi-core library for linear algebra, and back in the day there was very little in terms of portability to different multi-core systems that we could count on, and so we had to do our own layer. And moving forward, almost 15 years, and now the solution that we used back then now is tightly integrated in OpenMP and now extended even to accelerators. So in a way, seeing the good progress of OpenMP in that sense, we completely abandoned the work of trying to adapt to the architecture, and then we focused on standardization. So that's one leg in a way of the approach that we are using. The performance that we're trying to achieve and that we are expected to achieve from our libraries, from our users, comes primarily from the vendor kernels. So we're trying to collaborate closely with the vendors and make sure that that their kernels work very well, and we can utilize them. And oftentimes we prototype and release our own. Sometimes as research, sometimes as just reference implementations, and those eventually become, in a way, industry standards and get widely implemented by vendors because they are required by the algorithms that we implement. And finally, something that I argued in the white paper that is available on the workshop website is the productivity. So we have to achieve that with the limited resources that we have available to us, which is scientific programmers that know both the algorithms and the architecture. So focusing on the on standardization and the vendor support, we are able to in a way have the cake and eat it too, and get the productivity that we desire. But at the end of the day, we can only go so far. So we also rely on a lot of a tuning of our software. So we expose a lot of the features of our libraries as tunable parameters. In modern machine learning, you could think of those as hyperparameters. And there's a lot of research and both industry and academia trying to have those hyperparameters tuned as well as possible. Well, we've been doing that for decades now and exposing that to various tools. And so we welcome yet another way of tuning those parameters. And once those parameters are tuned, you can say that our software has been fully adapted to the platform. So that's in a way that the three-prong approach that we use. Thank you.
Yeah, thank you. Very nice. Yeah. So what I'd like to do next is maybe throw out a scenario, and maybe a few, but see what we have for time. So the first scenario is, so you have your existing software base. I think all of you are in a position now where you're porting to the Intel accelerator, right? Is that a fair statement, or making plans for that if you're not directly involved? Let's try to play that out and see, or maybe just say a generic accelerator that's not too different than NVIDIA GPU, right? So you already have, it's the same execution model, presumably the same set of algorithms should map to the new accelerator without, maybe with some tuning, of course, but not a fundamental algorithmic redesign. What are the steps involved in taking the software base that you have right now and then adapting it to this new accelerator type of architecture? Again, we can start with Hartwig.
Thank you. Yeah, so we just recently did that step, actually moving from only CUDA GPUs to also support AMD GPUs. And the process was extremely smooth. As I mentioned before, we have that library core that contains all the algorithms, and they remain completely untouched. They remain completely identical. What we need to do is we need to generate a new backend, a backend that is running on this new hardware architecture. And in this case, it was an AMD GPU, and we would need to write kernels for all the algorithms that are running on this backend. And fortunately, AMD did a really good job in writing a conversion tool, let's say, such that you could take NVIDIA or CUDA kernels, kernels written in CUDA, and they would be converted to HIP kernels. So kernels that are written in the HIP language that can be then run on AMD GPUs. And that worked really smoothly. So with very low effort, we could generate a new backend. And this is then automatically integrated into the library. So you have runtime polymorphism, and the algorithms can automatically run on that new backend. While that was a fairly simple step, you'll then still have some tuning that may be useful. So for example, the warp size on an NVIDIA architecture is 32 threads. On AMD hardware, it's called wavefront, which is basically the same, but it's 64 threads. So after that first step where we realized the porting and it was able to run on that hardware architecture, we then went into a second step where we said, okay, now we want to get the best performance possible on that new hardware. And what we did is then we did fine tuning of the kernels. While the first step is necessary to get it running, the second one, it is not necessarily needed. It's only needed if you really want to get the best performance. And this also means it is probably not necessary to do that tuning step for all the kernels, but only for the kernels that are really relevant for the performance in a certain application.
Yeah, very good. Now, so HIP is, I think, a particularly straightforward transformation from CUDA. Moving to Intel will require something more substantial, I think, right? Because, for example, I think the preferred model there is DPC++ with Pickle. Do you foresee it, presumably at least a bit more work for that back end, right?
So yes and no. So we're the US Exascale Computing Project is a great platform to talk to vendors, and we are in discussion with Intel, and they will provide, or they already do provide, a tool similar to the script provided by AMD that allows to port code from CUDA to Intel or to DPC++. While we don't have any experience how well that works in terms of performance yet. So what we need to do is we need to get access to hardware, run the kernels, and then see how good can we do if we actually hand tune these kernels. So that is totally true. It is a little more effort because it's something new, but in general, the workflow will be just the same.
Okay, very good. And roughly how many kernels does Ginkgo have that you have to pay attention to support the algorithms that are on top of them?
So actually, it was for moving from NVIDIA to AMD, it was a fairly small amount of kernels. So in particular, what we had to pay attention to is cooperative groups, also because the HIP ecosystem did not have the same coverage as CUDA. So we had to handwrite some of the kernels, but in the end, it was probably 2 handfuls of kernels that really needed additional attention. And most of the stuff can be converted automatically, respectively. In the conversion, you already anticipate, okay, we move from a warp size of 32 to a wavefront of 64. So wherever we use the warp size as a parameter, we replace it with a wavefront size of 64.
Very good, very good. Thank you. So
and
Steve,
maybe I can add one statement.
Yeah.
So I was really surprised. I have one person of my team. I asked him to basically explore that AMD backend, and after 3 weeks, I asked him how far he went, and he told me, yeah, I'm almost finished. Like 2 days later, he was done. So that was extremely efficient, extremely smart person. I'm blessed to have people like that on the team.
Very good, thank you. So Siva, Nathan, what about in your situation? How would things evolve, or how have they evolved?
So let me answer the big picture question, and then Nathan actually knows 2 aspects of it, which is how on the application side and on the Cocos side. So he covers both ends of the spectrum. From the big picture, when a new hardware comes, we think of 3 levels of conversion. One is at the bottommost, something like a programming model has to be adopted to that particular architecture. Number 2, a slightly higher level where kernels that are key to performance in the applications, this is like kernels that would take 20% or 30% of a particular application. When you look at the profile, adopting that kernel to an architecture, and finally adopting the application itself to an architecture. And the effort involved is quite different at different levels. The effort involved in Cocos is quite a bit, and Nathan can explain what are the troubles that we face, for example. Cocos kernels, we get little less trouble than that because we have adopted Cocos. And the applications, the ideal scenario for an application is change a template parameter and you are fine. It is mostly not that way. It is usually they face some issues as well because they have portable kernels and they have to tune a little bit as well. So the effort to change and adapt to an architecture gets easier as you go higher up the stack. Nathan, do you want to talk about what needs to be changed typically in Cocos and typically in Cocos kernels when you go to a new architecture and so an application at the Trullinos level?
Yeah, I can add some details there. That was a great summary. And we definitely have some overlap with some of the aspects that Hartwig mentioned, for example. So at the bottommost level, the Cocos programming model would have to provide a new backend. You could use that terminology also to support the native programming model of the new architecture that would come out. So for example, for AMD GPUs, there need to be some support for either the HIP programming model, or OpenMP target is another option for being able to offload to GPUs. So that would involve some incremental adaptation, I guess, that would require first making sure that the native data structures in Cocos are compatible with the new programming model that would need to be supported, and then moving on to the different parallel execution type patterns that we support. For example, parallel for, parallel reduce, parallel scan, or tasking, as these are the patterns that people that use Cocos would write their codes towards. And at that point, we'd be able to add support for the new backend within Cocos kernels, and then start doing testing there to see what's working and what isn't working, what needs to be modified in terms of the various kernels that we support. And then the next step from there would involve some performance tuning. We have some reproducibility numbers, so we have some sense of what to expect for different kernels on different architectures. And then moving on to the final stage, like Siva mentioned, when applications adopt Cocos and Cocos kernels with this new backend, ideally it would just be a matter of adding a configuration option within the build system and changing a template parameter to enable the new backend, but it's never actually quite that easy. But ideally, that's what the scenario would look like. Is there anything I missed, Siva, that I should expand on?
Nope, I think you covered it well.
Okay.
Yeah, thank you very much, Nathan. Piotr.
Yes. So in our land of dense numerical linear algebra, in the plasma library, because we used to be in the business ourselves back in 2006 in writing our own runtime, we would have to port the runtime to a new architecture. And right now, because we fully rely on OpenMP and OpenMP tasking for asynchrony on the CPU side, that's taken care of. And the major vendors, including NVIDIA, including AMD, Intel, and let me also mention IBM and the PGI as a separate entity, even though it's been required by NVIDIA. They're all the compilers are very, very good at tracking and participating in the process and OpenMP standardization and implementing it on their hardware. So in a way, we just sit and wait. So that's an approach of porting the OpenMP part between the architecture. So that's in a way that the business that we want to be in. But in the meantime, we don't really do the sitting. We actually try to discover what the architecture has to offer. So we try to see what would be the good parameterization of the kernels that we have to support on the devices, and so making sure that those the vendors deliver those kernels when we need them. And if they don't, I mean, in the meantime, we always try to supply our own versions of those, and sometimes we would need to get our hands a little bit dirty with some lower level tools that the vendors provide, but that gives an excellent starting point for the vendors to actually look at what we did and maybe even improve internally with their internal knowledge of both the tools that they give us and the hardware that those tools are used for. So so that becomes a process. And after all this is said and done, we can try to establish some good set of parameters that differ from one architecture to another. For example, the essential parameter for plasma would be a tile size, and then that is different depending on the device, whether you're targeting a CPU of a particular vendor or whether you're targeting an accelerator, GPU accelerator of a different vendor. So having those presets shipped in the library is important, and so trying to get those presets right is a matter of tuning, and as the tools mature, it might also be adjusted a little bit but yes, that's the process of porting. And the end, the very topmost level of the library stays almost the same. It tries to resemble the legacy interfaces from BLAS and then LAPACK, and the scheduling comes from OpenMP, and the lower level kernels hopefully will be supplied by the kernel by the vendors themselves, or by us, depending on what the need is at the moment. So that's a summary, and let me know if you have any questions, Mike.
Yeah, thank you very much. Those are really nice summaries. So let me see if I can make a few observations and confirm with me if they're accurate. From what I understand, listening to all three approaches, there is a definite algorithmic separation. There is a layer that you can express at a mathematical level of description, like you'd write in a paper, perhaps, say a Krylov method or a dense factorization method. And that code can remain largely unchanged as you go from platform to platform. You may need to tune it, for sizes and things like that. But essentially you can invest in that code and keep it pretty stable across platforms and across time. And then below that is a layer of software that needs to be customized for the specific architecture that you're targeting. And that would be the device specific code. Is that a fair statement for all three approaches? Would you agree with that? Or are there any nuances that I missed in that statement?
No, Mike, I think you summarized that pretty well. The differences are, or I would even argue that the approach that is presented by Peter, relying on OpenMP, is very, very similar to the approach that is presented by Siva and Nathan, except for OpenMP is replaced with Cocos. We are maybe a slightly different, but only in the aspect that these backends, we write them ourselves, and we do not rely on a different portability layer, with all advantages and disadvantages. So the advantages are, we have it in our own hands and we can focus on specific kernels. The disadvantages are obviously, it is a lot more work. So in terms of sustainability, I would argue, and productivity, it's better to rely on a portability layer where you can basically trust others that they will do the porting effort.
Yeah, thank you. Go ahead.
The one thing I would like to add is what you said, to go on top of it. Some of these abstractions are mathematical, where we would write it in a paper like a Krylov solver. Some of it is programming patterns that we commonly use, and this has emerged over many years. And some of it is like from the CPU community style of programming that we carry around, but some of it is completely new. And one example that I would give is a team level kernel, and exposing it, thinking things in terms of what is happening in a big device, what is happening in an individual team, and what is happening in a thread, and go even further, what is happening in a vector line, right? So it is like thinking multiple levels of hierarchical parallelism where you allocate memory, and that interfaces and CS level abstractions have emerged because of these actually.
Yeah, that's great. Great observation. Piotr, any response to this so far? I'm going to ask the next question or make the next observation, but go ahead if you have anything to add.
Well, I don't think I have anything to add. In a sense, I am a subset of what other teams are doing, because both Cocos has an OpenMP backend, and the Ginkgo library has OpenMP implementation on the CPUs. So basically, we are trying not to be in the game, and so far it's been working for us as the OpenMP standard matures. So in that sense, no further comments.
Yeah, very good. So then another observation I have is the role of vendors, and this is, I think, a differentiator across the project. If I can characterize it, Hartwig, you don't have any direct engagement with the vendors, for the work that you're doing. It's a small set of kernels, so you don't necessarily need it. You might ask them, say a staff member from one of the vendors to help you with a problem, or confirm with them that this is a good approach. But otherwise, probably not, right? And you're okay with that because you just have a few handfuls of kernels that you need to work with. In the Cocos situation, I know from past experience that there is a fair bit of vendor engagement, porting Cocos to the platform, tuning it. There's a performance profiler that's a part of the Cocos suite now. And so there's a fair bit of vendor engagement. They don't necessarily hand tune specific kernels, though. They hand tune the patterns or adapt the, write adapters for the patterns of parallel for, reduce, scan, and task. But they don't necessarily hand tune specific kernels. And then in Piotr, in your case, you have, because dense linear algebra is such a core thing, and the most important kernels are well known and well supported by the vendors, you can essentially rely on the vendor. You may help them by exploring the design space for the kernels, which you've done very well over many years. But in the end, you can trust that they will provide good optimized versions of those kernels, and you come to rely on those. So is that a reasonable summary of the distinction, how the vendors play a role or not? Did I miss anything?
I think that it is. We just have to be honest. We don't play in the league that Cocos and Cocos kernels is playing. So we are definitely, it's a pretty young effort, 3 years old. We do have some interaction with the vendors, and ECP is a big help in that. But it's also that usually if you have an algorithm running well on a certain architecture, let's say NVIDIA GPUs, and you move to other architectures, say AMD GPUs, and it's not performing well, and you send them, look here, why is it not performing well? We did exactly the same. Can you figure it out? Then they are usually pretty helpful, let's say.
Of course, yes. You have that dynamic of competition to helping you, to help you. Excellent observation, Any other comments? Go ahead, please.
Do you want to take it?
Go ahead, Siva. You're more directly interactive with the vendors.
Sure, I can take it. So Mike, you alluded to it, and yes, we do quite a bit of work on this. And what I wanted to, and I'm really thankful to the vendors and to the staff here in doing this work, right? Because some of the effort, we see the successes in these efforts outside. We don't see the failures outside at all. So there is a ton of work that goes in where before the hardware comes in, we would start working on a particular backend, and then the hardware may come out. The backend, that programming model the vendor wanted to support may not be realized. They wanted to change the backend later, and it would completely become a total failure, right? So, and the external community, the applications, don't have to go to this effort to do this. And at the same time, I'm very thankful for the vendors to help us where we have our tools like profilers, our programming model, and our kernels integrated well within their the workflow that they do to release a hardware. Where we come in at a particular time frame, they start optimizing our parallel patterns, the kernels that we do, and in their libraries that they provide. So it is a very collaborative effort that is rewarding in the end, but it is also quite time consuming in terms of how much engagement is needed. And so far we've been able to do it.
Yeah, very good. Thank you. Thank you. Piotr, how about you? And how does what I said make sense or not?
Well, so our, as you mentioned, the vendor interactions are very well established over the years. And if you look at the, the teams mentioned the new ports to Intel hardware. Well, that relies on SYCL, and SYCL is a C++ layer on top of OpenCL, and OpenCL already has a very long history. It was actually initially started by AMD on their GPUs back in the day, and now they just moved to HIP, which is a little bit more object-oriented and less verbose version of OpenCL. So already then we had some established contacts with AMD and then influenced the development of OpenCL BLAS, which back in the day was completely brand new. And so now from these efforts came Rock BLAS, which is a lower-level implementation, and a HIP BLAS on top of that. And we're also working with the Intel team and their effort and what they call one MKL. So interacting with the Intel team on that and directly describing the issues that would come up and porting our libraries to the Intel hardware that feeds the process. And out of that comes, as you mentioned, Mike, those very well-tuned kernels that are based on the knowledge that we cannot possibly have because it's internal to the hardware vendor, but in the end benefits the end user, and we are just a messenger in the middle, trying to just provide uniform interface, but underneath use the best capability we can get our hands on. Very good, very good.
We've spent a lot of time on this, and I don't want to linger too long. For me, this has been a fascinating conversation, and I'm hoping that the viewers will be able to gain something and see what I think are three very legitimate models for developing and supporting portability, performance, and productivity across a software ecosystem, and depending on the characteristics and the current nature of your situation. So I appreciate your time participating in this conversation. I want to give you each a chance to just make any last comments if you want. Maybe again start with Hartwig, and anything you want to say. If it's all been said, you can say that too.
No, thank you, Mike, first of all, for having that opportunity here in this panel. I think it's a very good experience. And I guess my message out there is for all the people that are developing software, have portability in mind. I think this is the most important aspects when we are moving forward into the future with new hardware architecture designs, with new processors supporting different number formats and whatever. I think portability is the key for making software sustainable.
Thank you, thank you. Siva, Nathan?
Nathan, you want to go first?
Yeah, thanks for having us, Mike, and thanks all the panelists. This was a great discussion. Go ahead, Siva.
Yeah, thank you, Mike, and thanks everybody for having a wonderful discussion. The one final thought I would point out is I like thinking it in terms of portability, in terms of abstractions, and the abstractions help productivity quite a lot. And so this is something that we have learned over years, and we kind of preach now when we work with an application. And as Mike mentioned, all of these models are legitimate models based on somebody's use case. If you have a handful of kernels, you can optimize all your handful of kernels in different architectures. You could scale out and try to support as many applications as you want, or you work with the vendors and improve programming models and libraries, and with the vendors and wait for that to improve your own library or the application, right? So and we all collaborate in and exchange ideas with each other. So this is a wonderful community to work with.
Thank you very much, Piotr.
Yes, so I would like to echo what Hartwig and Siva and Nathan said. So thank you very much for having me here and listening to what I have to say. And if I could add one more noun to the things that Hartwig and Siva mentioned. Sure. So Hartwig mentioned portability, Siva mentioned abstractions. I'm going to mention standardization. So standards have it's a two-sided sword, but they tell us what we agree upon, but they also tell us what we didn't manage to agree upon, and things that are left out of the standard are also interesting, because this is kind of where the abstractions and portability would come into play, and it would be required to make it happen. So standards are also very important, and that's what we rely on. So yes, thank you very much again.
Yeah, absolutely. Thank you. Very nice comments. Well, thank you all for participating in this conversation. I think this will be a very nice contribution to the workshop and for going forward too. I think there's been a lot of very nice comments made here. So thank you all.
Thank you, Mike.
Thank you.